An exponential function is a function whose has an exponent in it. At this time, our base is a number and the x's are in the exponents. So a quick example of something like this might be like f of x is equal 3 to the x squared plus 5. So notice the base of our exponential is a number and the x's are now up in the exponents. So since we got this brand new type of function, let's see what it looks like. So let's see if we can graph a very simple exponential function. Anytime we don't know how to graph something, we always just make a table of values and plot a whole bunch of points. Since I want to know what this thing looks like, let's pick a bunch of values right here around the origin. So for each one of these x values, I need to plug it in here and figure out what our y value is. So let's do a little bit of side work here real quick. So if x is -2, that means y is equal 2 to the -2 power. Now remember your rules for exponents. We can't directly apply a negative exponent. We have to make it positive first. The way that we apply a negative exponent is you have to move it. Remember, a negative exponent takes whatever is being raised to negative power, moves it to the opposite side of the division bar, and then that exponent becomes positive. Now that we have a positive exponent, we can apply that, so that would be 1/4. So now we have 1 point on our graph, -2, 1/4. All right, so if it's -1, so we get 2 to the -1 power. Same idea, we can't apply a negative exponent, we need to move that. So our exponent becomes positive, and that is just 1/2. Now the rest of these will probably be pretty easy to do just by looking at it. Anything to the 0 power is 1. 2 to the first would be 2. 2 squared would be 4. All right, we have 5 points up here. Let's see if we have enough to kind of do a quick sketch and see if we can figure out what the entire graph looks like. All right. All right, so let's plot our points. What do we have? We have if x is -2, so we're here, y is 1/4. Now just get close, kind of approximate, so that's down right about there. -1's 1/2, that's a little bit higher than that. 0, 1, that one's easy. 1, 2, 1, we're up at 2, and 2, we're all the way up at 4. So as of right now, I'm going to go ahead and connect these 5 dots. That's what we know what the graph looks like. Let's see if we can reason out what happens as we keep going. So as x keeps getting bigger and bigger and bigger, so if this was 3, 2 to the third would be 8, then 2 to the fourth is 16, 2 to the fifth is 32. So you can see that this thing is growing, and it's growing pretty fast. So that's going to keep going up like that. Now if we go this way, it's kind of the same thing, but you get the fraction. So at -3, that would be 1/8. -4 would be 1/16, 1/32. Now that keeps getting smaller and smaller and smaller, but never actually gets to 0. So we never actually touch that x-axis. In fact, the x-axis here, and I'm going to do it just below, is actually a horizontal asymptote. So our exponential equations have a horizontal asymptote that as we approach one of our infinities, either negative infinity or positive infinity, the graph is going to approach that. In the other direction, it's always going to be heading up or down. All right, so that's the basic shape of any exponential graph that has this basic form. Now, just like we saw from a couple of sections ago, we can shift this thing all over the place. By adding and subtracting things, we can shift it up, down, left, and right. By putting negatives in either front of the function or in front of the x, we can flip it on the y-axis, or we can flip it on the x-axis. So this can be flipped all around. So you have the basic idea of what an exponential graph should look like. So for graphing these as of right now, just plot a few points so you can get the basic shape of the graph and sketch it real quick. But generally what's going to change on these is what base you're going to use. Here we used a base of 2. Well, there's 2 bases that we use a lot more than any other bases. So most used bases. Now the bases that we use the most in math are base 10. That's because, well, our number system is base 10, and this is called the common base. That one's pretty straightforward. The next one's a little bit weird. It's the number e. Now I'll put a letter here because, well, I can't write it down. This is called the natural base. Now this e here is a number. Now I got to use a symbol for this because this number is an irrational number, kind of like pi. It goes on forever, never terminates, and never repeats. But e is approximately the number 2.71828, so on and so forth. Actually, it kind of looks like it repeats there for a second, but it doesn't. So anytime you see this number e, you're like, oh, that's about 2.7-ish. So since this is an irrational number, any homework problems that you run into using this number e, generally you're going to have to use a calculator for. And somewhere on your calculator, normally it's a shift button on most calculators. You'll see a button that says ln. In the shift on there, you'll see e to the x above it normally. So if you have any problems with e to the x, you're most likely going to have to use a calculator. All right, so we got these exponential functions. We've got a basic idea of what they look like. From the picture, it should also be able to, we should easily be able to see what would the domain of your basic exponential look like. Well, domain is the x values, and you can see no matter if we flip this upside down, this way, left or right, or shifted it up, down, left or right, the domain's always going to go from negative infinity to positive infinity, no matter what. Now the range will change depending on which way we shift this, up and down, or if we reflect it. But just for our basic graph, this was just a number to a variable, the domain's going to go from 0 to infinity. Now this will change depending on the graph. Right, if we have some shifts or some reflections, the range might change, but the domain for these are always going to be negative infinity to positive infinity. All right, there's a lot of uses for exponential functions out there. Probably the one that you're going to see the most, and you should have probably seen earlier on, are interest problems. For interest problems, we start out with something called simple interest. And hopefully you've seen this formula before. The amount of interest you make for simple interest is the principal times the rate times the time. Interest, principal, interest rate, and t is time. And for most of these formulas, time here has to be in years. Really what t stands for this time is the number of times that the interest is applied. Now simple interest is based off of when you only make interest on the original principal that is used. Now remember, principal is either the amount that is borrowed or loaned. Now simple interest we don't run into a lot. The type of interest we normally run out into is called compound interest. The compound interest formula, well, it's a little more complicated. It's a is equal to P1 plus over n raised to the nt. So here, this isn't actually telling us directly what the interest is. This is actually telling you the value of the account, or the amount of the loan, or whatever. P is still principal. R is still our interest rate. N, that's a new letter up here. N is the number of times compounded per year, and T again is time, and again it has to be in years. So if you're given your time in months or weeks or days, you're going to have to convert that to years to use this formula. Now the good news is this is just a formula. So once you figure out what the principal, the interest rate, and all that is, you plug it in, put it in your calculator, and it gives you the answer. Now, there are a few things that may confuse you. When they tell you the number of times compounded per year, generally they give this to you in words. So they'll say things like annually, here I'm going to what N is. Annually means once. Semi-annually, N would be 2. Let's see. Quarterly would be 4. Let's see, what about next? How about monthly? Of course, would be 12. Weekly is 52. Daily gets a little weird here. Doesn't look like it's spelled right. Daily, of course, 365 are how many days in the year, but a lot of textbooks, including a lot of like accounting books, use 360 for the number of days in the year. So a lot of times, application books may not use 365. I would suggest using 365 because, well, that's the actual number of days a year. So for all of these, you just plug in all the numbers that you know, the amount that's borrowed or loaned, the interest rate, the number of times compounded per year, which you can get from generally is told to you in words, and the time in years. And that'll tell you how much you have in the account. Now, the difference between compound interest and simple interest is compound interest, you're getting interest on your interest. So let's say that you put some money into a savings account that gives you interest every month. So you put $100 in the first month. The first time they pay you interest, they're going to pay you interest just on the $100. Let's say they gave you $1. It never was, never that much. So the next month, when they go to pay you interest, they don't give you interest on the original $100. Now they give you interest on the $101. So now you're making interest on your interest. Now you'd think that the number of times that you compound per year would mean that you make more money. Well, you got this offset pattern that happens here. The number of times that you compound per year does increase the amount that this thing gets multiplied by itself, but your interest rate, because the number of times is increasing, gets smaller and smaller and smaller. So there is a cap to how much you can make with this, and it's called continuous interest. And it's really what happens to this formula as n goes to infinity, basically, as n gets bigger and bigger and bigger. And the amount in the account is the principal, e raised to the RT. So there's that e number that we saw earlier. And again, all these are the same thing. This is the value of the account. R is your interest rate. And T is still time, and you're going to want this in years for this formula. All right, so again, once you figure out what these values are, plug it into the formula, plug it in your calculator, and you'll get your answer. So exponential functions, you're going to see lots of places that these are useful for. The interest formulas are just one of the first places that we see them.